So I'm going to talk about machine learning library for Python. So it is Python, so it's not like pure functional, but this library is very functional in its design. And that's what I like about it. And so it's called JAX. JAX is the name of the library, and Flax is the name of the neural network library, which is built on top of JAX. So it's like the neural network library is Flax plugged in. And yeah, so JAX stands for JIT, AutoGrad, and XLA. So JIT, probably you all know, is like a just-in-time compiler, so it means it's going to compile when you run it. AutoGrad just means that we can get the gradients without having to manually write the gradient of all the functions that we implement. And XLA is the the machine language, or the intermediary machine language of TensorFlow. And so when we JIT, we're going to JIT not to machine code, we're going to JIT to XLA. And once we have XLA, we can execute it on CPU with the vector instructions, or on GPU, or on TPUs. And so that's what we need, because we're doing deep learning, we need to do a lot of compute. So before I go further, I guess everyone probably has used Python. Yeah? Has anyone trained a machine learning model? Show of hands. Okay. Quite a few people, yeah. Good. All right. So there's going to be a little bit of code and a tiny bit of maths too. So these are the key parts of JAX. So we have a grad function, which it takes a function and returns a function. And the function it returns is going to compute the gradient of the function you gave it. So already you can see it's very functional design.
F prime.
It's F prime, yeah. Except Python, you can't have a prime. And then we have a JIT function, which returns a function that computes the same thing, but compiled. And then we have VMAP and PMAP, which I'm not going to talk about today, but basically all they do is they return a function that computes the same thing, but on a collection of inputs. And when you can use the GPU or the vector instructions, it will do that.
What's the difference?
The difference is VMAP is going to use compute everything at once, and PMAP is going to try to parallelize cross cores. So I've only ever used VMAP, actually I haven't used PMAP. I think perhaps PMAP can do across nodes as well, but I'm not sure. And then another key ingredient is we have jax.numpy, so it's just a drop-in replacement for numpy, if you use that. And people usually do import as JNP, and then basically everything that you had in numpy is going to work in JAX. And then we have a jax.array, which is like the numpy ND array, except it's immutable. So you can't modify the first element. You can only basically make a copy and change things as you copy. Which sounds inefficient, but if you're combining it with JIT, then the JIT can sort of say, oh yeah, you copied this, but then you never used the old one, so I can just do it in place. So it's not an efficiency concern, as long as you're doing the JIT. Okay, so I'm going to talk in 4 parts. So first, going to look at models as functions, not objects, which is basically a comparison to PyTorch. Then I'm going to look at the gradient descent update in each library. Then I'm going to talk about this nice sort of design pattern that they use in Flax to define neural networks. And then at the end, I'm going to go into the weeds a little bit and talk about what happens when we actually do need states, so the functional library gets a little bit messier. Okay, so when we're doing machine learning, we're basically always trying to solve a problem like this. We're trying to find theta that minimizes some objective function. And this objective function is higher when the error is high and lower when the error is low. So you have a training set and you want to minimize the error on your training set. And theta is the parameters of the model. So for a convolutional network, it would be the weights and the biases at every layer. So it's it might be 10 million dimensions. So here, this is a 2-dimensional function, or function on R2, but we're going to have 10 million dimensions. And so the form of this objective function, E of theta, it's basically going to be an average over some training set. So we have a training set which is X, Y pairs. So you can think of it as line fitting, but maybe X is the image and Y is label for the image. And F is our model. So our model is going to take parameters theta and an input x and produce an output. Then L is the loss function. It's going to compare our output to the desired output. And then we're just going to take the average of that over some data set. So it might be 1 million examples of n. And we want to basically minimize that function. So I think this is, it's the second last slide with equations. And so how we're going to do that is by gradient descent. So that's this last theta t plus 1 equals theta t minus the learning rate times the gradient. So the motivation here, okay, that's better. The motivation here is we're starting at theta t. We're going to compute the gradient, which tells us the direction to increase the function, and we're going to go in the opposite direction. So we're going to do minus some constant, this is called the learning rate, times the gradient. And that's going to give us a new theta. So then all we need is an initial theta 0, and we can just run this step. And as long as we choose the learning rate reasonably, we should get to a minimum. It might not be a global minimum, it might just be a local minimum. But this is basically all we want to do. Yeah. Where this grad E is the gradient of the average loss of the ConvNet applied to this data set. Okay, so you can immediately see why grad is important, because we have this big complex function and we need gradients of it. And also this theta is like 10 million parameters. The inputs are like images. So it's also important to be efficient. That's why JIT is important. Okay, so on the left we have the PyTorch code, and on the right we have the JAX code. So they're actually very similar. So don't worry about the constructor for now, I'm going to look at that later. But basically we call this constructor, and then in PyTorch, we can immediately, we can run the model on an input. Like we didn't train it yet, so we're just going to get like garbage. But say we had trained it, this is how we would evaluate it on some new inputs. So this X, I've put X's because it could actually be multiple inputs, and then it'll give us multiple outputs. So that makes a lot of sense. We evaluate the model on the input. In JAX, it looks slightly different. So we define our model, but then we can't use it, like it doesn't have the parameters built into it. So then we need to call model.init, giving it a random number generator, and it's going to return a theta. And then when we use the model, we can't just do model of x, we need to do model.apply to theta and x. So you can see that's what I mean by object versus function. Like in PyTorch, the parameters are kind of like inside the object, the model. And in JAX, the model is like, it's a definition of the function form, but you still need to give it the theta as an input. And that's kind of nice because you can like manipulate this theta as you like and do all sorts of crazy stuff. And what that theta actually looks like is here at the bottom. So it's basically just a Python dictionary, or like a nested Python dictionary. So we're going to have, these are the 4 layers of our neural network, and then each one has a bias and a kernel, and then the value is one of those JAX arrays. And so this is just a native Python dictionary, so it's easy for us to manipulate, whatever. All right. And so you can see that already, like say if we wanted to like make a copy of our model, if we're in PyTorch, we need to do like a deep copy, like all the constructors of all the child classes, like the member classes. But in JAX, we can just like copy our theta, this is just a dictionary, and then we can change it. We have 2 models. Like it's kind of much more convenient to do creative stuff, I would say. Okay, so how do gradients look different between the 2? And by the way, like by the end, you might just think like, oh, just PyTorch looks great. Actually, it looks so easy. And it is kind of a bit easier to do simple stuff in, but JAX like gives you more power, I would argue. So to do gradients in PyTorch, we first need to do model.0 gradients. So it's going to set all the gradients to 0. The gradients are also inside the object. Then we compute the loss. So this is a PyTorch loss function, comparing the output of the model to the labels, y, like the ground truth, the known desired outputs. Then we call this loss.backward function, which is going to compute the gradients starting at the end going backwards. That's why it's called backpropagation. And after we do this, we have the gradients, but they're sort of inside the model as well. So if we look at model.conv1.weight, it's a torch.parameter object, and it has a .grad member, and that's where the gradient is. And how PyTorch knew to compute a gradient for that conv1.weight was because it also has a requires grad member, which was set to true. And so if you want to change what you were computing the gradient with respect to, you need to go through and set that one to false, set the other one to true. So you can see it's very object-oriented. Like it's got a state is built into this model class. Okay, and in PyTorch, sorry, in JAX, it looks very different. What we need to do is we define our objective function. So it's going to be the mean of the loss of the comparing the y's and the valuation of the model. And then we can just use jax.grad to get a function that computes the gradient. So here we're using jax.grad, it takes a function and returns a function. And grad will always do just the gradient with respect to the first input. So if you want to do multiple arguments, you have to put them together. So the x's and y's here are not, we don't get the gradients with respect to those, just with respect to theta. And then to compute the gradient, we call grad functions. Grad equals grad function, and it's the gradient at theta with x and y as extra inputs. And then we have a grad dictionary, which kind of resembles our theta dictionary. It has just the exact same structure with an array, and the array gives you the gradient for each of those parameters. And this looks much more like the mathematics, where like the gradient is a function that maps Rn to Rn. So it's kind of like more mathematically same. And so, yeah, this is kind of like, I'd say this is more familiar to mathematicians, and PyTorch is probably more familiar to like people who've just come out of undergrad, you know, knowing like imperative programming inside out. The next part to look at is how GPU acceleration works in PyTorch. So again, it's kind of straightforward. So you just do model.toCUDA, x's and y's to CUDA, and then you use the model as you did before. So you call model on inputs. That's going to happen on the GPU now. And if you're doing the gradients, also the code is exactly the same, but because you did .toCUDA, everything's now on the GPU, and this will happen on the GPU. So PyTorch is very convenient. And then if you want to move it back to the CPU, you need to do .toCPU. I guess then if you're using like Metal, like the Apple shader stuff, then maybe you need to change this CUDA string to something else. Maybe you don't need to move it because it's shared memory. I'm not sure exactly what the PyTorch Metal support is. And in JAX, we just do this. So we do JIT of a function to get a function, and then we call the JITted version. So I'm also showing that you can do it with lambdas as well. So I'm JITting something which takes theta and x and applies a model with parameters theta to x. And we can do the same thing, we can compose JIT and grad. So we can do JIT of grad of objective function, and then we're going to have a function that computes the gradient on the GPU, and it's like compiled there. And so it's exactly the same then to use it. So this is like quite elegant, I'd say.
Sorry, at which point did you declare here that we want this to go to the GPU?
So here it's not declared, yeah. Basically, the jax.jit will just use whatever devices it can find.
Okay, that's restriction.
Yeah, yeah. So I think there might be a way to constrain it to only use like this GPU or this, I don't know what else, TPU, or you can like, you know, hide the GPUs from it. But I think that's part of the XLA, is that it kind of has this built-in thing that determines how to optimally schedule stuff using whatever you have. But you do lose control in a way. And also, like, you kind of can't put stuff on the GPU and leave it there. Like, the JIT function will take your array on the CPU and like move it to the GPU, do everything, and return the value. I don't think you can explicitly move something to the GPU. It might leave something on the GPU until you use it afterwards, But yeah, you do lose a bit of control in a way. I think it's also possible to look at the decompilation of the XLA so you can see what the instructions are. I'm not sure how much fine-tuned control. Did anyone use TensorFlow 1, perhaps?
1?
Yeah.
Well, that's when I started my PhD, yes.
Yeah? It's quite horrible, right?
Oh,
yeah,
don't remind me. A few days to install it.
You had to define the graph, and then you had to call the graph with a p-dict. Yeah. Basically, this is doing the TensorFlow 1 graph construction in newjax.jit. So how does JIT work? So basically, it's not really how it works, it's more like how do you use it. So the arguments and the return value of your function must be something called a pi tree, which is either an array or a list of pi trees or a dict of pi trees. And so you can have lists of lists, lists of dicts, dicts of lists. Basically, you can have these kind of fundamental Python data structures. You can put arrays in them, and the JIT will work, and grad will work as well. So that's quite nice because for our comp we had 4 layers, and each layer had 2 parameters. So it's quite a natural fit for a dict of dicts. Okay, and how it works is the first call will be slow. So it's called JIT, but it's a little bit generous because it might take something really complex, if you're doing second gradients of a big network, it might take 30 seconds to JIT. And that just happens the first time you call the JITted function. And then it caches the TensorFlow graph. And the next time you call it, it's going to be very fast. So here I've got this train step was taking 0.3 seconds. The second call on CPU was taking 0.04 seconds. The second call on GPU was taking a fraction of the time.
Sorry, so is this the people who are researching optimization?
It is really good for people who are researching optimization, yeah. As in mathematical optimization of a function, not computational optimization. Yeah.
Otherwise,
yeah, and for really practical stuff, there are a few cases where it's, I don't know, there are a few things which are easy to do in JAX, which have had to be manually added to PyTorch, but they are manually added. So if you're just using them rather than inventing a new one, then yeah, PyTorch is good. And I think all my PhD students use PyTorch. My evangelism has not worked. All right, and you can use any JAX function you can JIT, you can take a gradient of. You need to be a little bit careful if you have ifs and whiles, because how that first run works is it's basically going to replace the arrays with some tracing object that builds up a trace of how it gets used. And if you have an if statement and you go down one branch, then you're kind of not actually tracing the conditional. So there's a JAX.conditional to do that. It's okay to have if and while. Yeah.
If they're going to work like a side effect, so it cannot properly track.
Basically, so if you put a print statement in your function, then when you call it the first time, you'll print something. When you call it the second time, it won't print anything. Because the first time, it was just basically finding the computational path, the DAG of this is a function of this, this is a function of this. And when it does that, it will only go down one branch of the if. Or it will run the while statement n times. And then the thing you compile is going to be running the while statement n times, even if the condition changed.
Yeah.
This is only when the if and the while depend on the result of the computation. And actually, it will throw an error if you try and do that.
Except the one has also its own if and while.
Exactly. It's exactly like that. Yeah. So this is that's due to the way that it does the JIT. But if you have something like a list comprehension or a dictionary comprehension over your data structure, that's fine because it's not going to change. It's really just when the condition is changing based on the inputs that you need to use the custom while loop and if statement. All right, so now I'm going to basically put these pieces we have together to do a full gradient descent step in PyTorch versus in JAX. And so just for a reminder, here's the gradient step we need to compute. So we're going to get a new theta. We're taking our old theta and subtracting the scalar times the gradient. And so here's how it looks in PyTorch. So we have an optimizer object as well as our model object. This is like, the type is like torch.optimizer. We're going to take some x's and y's, and what we're going to do is zero the gradient, compute the loss, loss.backward, and then optimizer.step. So you can see it's very simple and clean, but also like we kind of can't see where the information is flowing, you know. And then, so once we've defined that function, we can just do model.toCUDA optimizer, and create an optimizer which gets basically a reference to the model's parameters. Here it is. Set the learning rate in there. And then we're going to loop over the examples in our data set, move them to the GPU, and call this train step function. Does that sort of all make sense? Any questions? So it's just really the bit we saw before about computing gradients, but with this extra optimizer object. All right, and in JAX, here's how it looks instead. So we have this optimizer object, but it doesn't contain any state. And then our train steps, we're going to use like a decorator here to basically call JIT on the function after it's defined. If anyone's not familiar with Python, this at basically means like call JIT on the whole function and return that as the definition of the function. So we get the gradient function, evaluate the gradient function, then we call optimizer.update, and this takes a gradient and an optimizer state, because the optimizer itself has some like memory of the previous steps. And that's the same in PyTorch, it's just hidden. So we update the optimization state based on the gradient and also get some updates. Then we're going to apply the updates to theta to get a new theta, and we return the new optimizer state and new theta. And then we need to initialize the optimizer state, and then we go to the dataset and do state theta equals function of state theta and data, which kind of looks a lot more like this function, I would argue, like this expression. Except like here, you can't see the optimizer state, yes. And yeah, that's basically it. So just to show you the PyTorch again, it's kind of much cleaner, but to me, I prefer the JAX just because I know what's happening to my theta, I know where it's getting modified, I know that the optimizer has some state, yeah, it kind of lets you do a bit more. So why is this like stateless form good? So it's easy to do some wild stuff. So you can have multiple theta vectors. You can like take the gradient with respect to the input rather than theta, which you can do in PyTorch too. It's just very fiddly. You can apply weird transforms to the gradients. So people do things like projecting the gradients, normalizing the gradients, averaging gradients from different data. Yeah, that's another point. So it just kind of gives you like total freedom over how you're doing your updates, which is maybe it's probably best suited to research, I'd say. Whereas like if you just know, I just want to use deep learning, I've got my data set, then PyTorch is probably fine. PyTorch and TensorFlow are kind of good if you're not experimenting with the algorithm. It's also good for distributed training because kind of made the state explicit, so you don't need to make sure that, that everything is happening correctly. And this is kind of my message, I don't know. The message I take from this design of JAX is that having the abstraction that aligns with the mathematics basically lets you do whatever you want to do, rather than just being like a hammer for one. Another reason is that you can do higher derivatives. So we looked before at the grad E, which is the derivative of E with respect to theta, and that's a vector. We can also consider the second derivative, which is the derivative of the derivative, and that's going to be a matrix, which is n by n. The problem is that n was like 10 million. So if you do 10 million by 10 million, it's basically like having 10 million copies of your model. But there's a cool trick you can do, which is you can compute Hessian, this H is called the Hessian. You can do Hessian vector products. And you write that basically the second derivative times a vector is going to be the first derivative of the derivative inner product with a vector. And this thing is a scalar, so you can take the gradient of that, and then you get your vector, and you never have to construct this huge matrix. And how we write that in JAX is like, we want the grad of a function. It takes the vector dot product between a gradient and a vector. And that's it. It's kind of like something that would be very difficult to do in PyTorch. And these second gradients are important because it tells you not just like the slope of your function, but how the slope is changing. It's like a curvature. So you can know like, yeah, like the slope is going down slowly here, but if the curvature is low, I can still take a big step because it's not changing very much. But yeah, sorry about the maths on this one.
So is V going to be the parameters?
So V here is is what you call like a tangent. So it has the same dimension as the parameters. But what you might actually use this for is there's some research which shows that the maximum eigenvalue of H determines how well your model works on new data.
Oh, wow.
And to do like to get the maximum eigenvalue, you can find that by just basically taking a random vector, multiplying by H, multiplying that by H, multiplying that by H.
Well, it approaches.
And it approaches the maximum eigenvector and eigenvalue. This is like the PageRank algorithm. It's like you basically keep multiplying and you eventually get to like this the biggest denominators. So that's where that's really useful. Yeah.
So which optimizers use this behind the scenes?
I think none of the popular ones. Yeah, because it seems like the effort required to get the second derivative is usually like so it makes the step take much longer. Like maybe the second derivative might take, I don't know, twice as long as the first derivative, which is pretty fast, really. But also you need to do this iteration, and it's not so fast. Usually the advantage you get from considering second order optimization is kind of trashed by what you could have done by just taking like 10 steps of first order gradients. There are some particular cases like maybe like NERF, where you have kind of like a small network and you're like training, do you know NERF? It's like the 3D reconstructions, neural radiance fields, where you have like, take some images, you train a ConvNet to represent the scene. There's some research showing that you can use these methods there, and they do actually have an advantage, but for like the classic, like ImageNet, 10 million images, 1,000 classes, just need as much compute as possible, first order still kind of dominates. All right, so I wanted to talk about now what those classes look like. So this is JAX. So when we define the ConvNet, it is actually a class, and it's inheriting from another class, and it's got methods, and it's modifying itself. So when I saw this, I was like, oh, this is like not functional programming, right? Because of all this weird, like this stuff. Like it's got inheritance, it's class, it's got like modifying state.
You say this is JAX, that's PyTorch.
PyTorch looks almost identical. Yeah, this is JAX. Even like I think I even call it torch.nn module.
That's deliberate.
But there's a slight difference here, which is that what this stores is just the dimensions of things. It doesn't store any values. And each of these, like conv, and dense, are also modules. They also don't store any state. All they store is the dimensions of the operations that they do. Yeah, so they have like an apply function and an init function. And so you can call their init function to get the structure of their parameters that they need. Then you call apply function on what you got from init. And so since nn.module is composed of other modules, and none of the modules have any state, the whole thing kind of doesn't have any state. But you can still like get in there and like modify a self dot whatever and like hack it and totally break everything. But if you're using it as it's intended, then it's still kind of stateless. And yeah, just because I should probably just say quickly what it's doing. It's like basically applying conv, doing a value is like a nonlinear function, taking the average of the local areas, value conv again, taking the average over local areas, reshaping to a vector, then applying like a dense matrix multiplication, and then finally another dense matrix multiplication. And that is like a 4-layer content.
I thought this method should be called apply instead of call.
Yeah, so that's the other thing. So like the inheritance, like is also using inheritance, right? And so that apply function is actually something which is like inherited from the base class. But so basically you define the setup and call functions, and then it defines like the init and the apply functions.
So eventually you will be using dot apply.
Yeah, exactly, yeah. So it's not a typo, it is actually called call. But then if you call it, then it says like, hey, like, you're not supposed to call this, you didn't give me the right thing. Yeah. So I basically covered all this before, but yeah. Is it really functional? It's not really an object, it's more like a collection of closures over the configuration. So yeah, that's how I see it.
Which is kind of what a neural network is. So
Yeah, you can see that. Yeah, but sometimes you don't want to close. I guess PyTorch like closes over the theta as well.
and the gradients.
Yeah, and the gradients. Yeah.
If you look under the hood enough times, nothing is ever truly functional.
Yeah, that's right.
The computer itself is not functional.
Exactly.
Yeah,
Yeah.
actually,
Yeah. Okay, I'm not sure we have time. What's the time? Is anyone in a rush? I'll finish. Just got like 3 more slides, I think. So this was kind of an idealized situation where our only state is like the optimizer state and the theta. But sometimes we run into slightly more complicated situations. So sometimes we need randomness during training. So data augmentation basically means like if you have images, you just apply like some random transform to the image such that the label stays the same, but the image is different. And since you have randomness, that means you need like state, because otherwise you need like your pseudo random generator that's going to get updated when you use it. Also, like, dropout is like sometimes you just set some neurons to 0, and that makes it work better on new data. And that has to be randomly setting things to 0. Similarly, mix-up stochastic depth, they're like basically adding randomization during your training update to get better results on new data. The other one is batch normalization, which is still kind of a little bit mysterious. People don't know why it works, but it works. It works really well. You basically normalize the statistics of every layer to have 0 mean unit covariance. And then if you do that while you're training, convergence will be much faster. And then while you're doing that, usually you save those statistics so that then when you go to use your model, you just use the statistics that you saved. But basically you need to be logging these statistics somewhere. And in PyTorch, that just happens in the layer itself, it just updates itself without saying anything. But in JAX, you need to like return the statistics, like give it the old ones, and yeah. So when you start adding these things, you need state in your training step, and it starts to get a little bit ugly. So this is the train step again, but now my objective function takes some mutable vars. And when I call model.apply, I give it the params and the mutable vars. And it returns mutated vars. And then I'm going to return mutated vars. And then instead of calling jax.grad, I need to call jax.value and grad and say has auxiliary equals true. And then it's basically going to pass me the second output back. Oops. So yeah, it doesn't look so nice anymore after you've done it.
So that's just when you add batch normalization.
Yeah, you have to do this because you need to give it like the old statistics here and get the new statistics here.
At least on runtime, you fix those.
Yes, yeah, exactly. Or what you can do is like train without updating the statistics, and then at the end come back and just compute the statistics once. That'll work too. It's kind of similar.
I thought the whole point was to do it while you're training because it will enhance the whole
Yeah.
process.
Although then there's something a little bit messy, which is that you have like an exponential moving average rate, which you have to pick, which no one really ever talks about. Yeah, so it starts to get ugly here. But I want to talk about one other really cute thing, which I hadn't seen before. I think they might have added it to none by now, but it's this idea of splitting a random number generator. So basically what you do is say you've got your random number generator, which is started at some seed. I'm going to split it. Oh, I should have put a comma 3 here. Oops. But you split it 3 ways and you get 3 random number generators. Then I can give each one to a different function and they'll like go ahead without influencing each other. Because often we have like, the thing I always didn't like about random number generators is that they kind of like, especially if you use the global one, then if you add like, one extra random thing in that function, it's gonna change all the functions that get called after it.
Super random.
Yeah, and it's only pseudo random, yeah. I should have put the ER in G in. And so this is kind of like a nice technique where you can like take your own random number generator, split it, and then give each of your functions different ones. And that way, you know that if I change the first function, such that it has one extra call to the pseudo random number generator, it's not going to influence the downstream ones. So it's just kind of an elegant thing which I haven't seen before. Yeah. And yeah, I think that's the end. So yeah, just going back over what we saw, we have grad and JIT, which map functions to functions and can be composed. The model as a function of theta and x rather than just an object that stores the theta. NN.modules, which are kind of like objects that aren't really objects that use inheritance that don't really have it's not really inheritance. Yeah, when you have this auxiliary state, it's more explicit, but you pay for that with complexity. And so you can compare, like, this is my repository, which is basically training CFAR using Flax. And then this is like a PyTorch version as well, if you want to have a look. So I just baseline off theirs. And that's all. So thanks very much. Thanks. Happy to take questions.
That's very much mistake on things I saw Chalet tweeting that he's got a Keras variant called Keras Core.
No.
Jack's backend.
Oh no. So it's no. Yeah. So I think the problem with TensorFlow, one of the problems with TensorFlow is that this has kind of been documented online, that there were many different teams and like they all kind of like developed their own different ones. There's like Keras, there's like TF.slim, there's like Haiku, I'm not sure if it's Haiku or Sonnet, but basically like all these different wrappers around TensorFlow, but there's TF2, and it's just such a mess. And yeah, so that's kind of depressing if they made it Keras. So I guess now it's no argument there. What are you using? Well, it's Keras, doesn't matter what's the backend. So it's actually the DAX frontend with the Keras backend? Yeah. Okay. That's what the point is.
Well, they did the same thing with PyTorch. I guess people just love Keras syntax.
Yeah. The one thing I really did like too is these interfaces where they just do like model.fit. Yes. You can't even see the training loop. No, it's deep learning for humans. Yeah, okay, maybe an unusual perspective. Yeah. All right. So then I reckon we might head to the Belgian Beer Cafe and grab a bit of food and drink. Feel free to join. Feel free to come also just for a non-alcoholic drink too. And this might be, actually, I didn't cancel the one for next week, but I'm thinking I'll probably cancel the one for next week and just say this is the last event for the year.
For lack of space.
Oh, wait. Sorry.
Do we have anyone going?
There might be. Yeah.
Anyone? Okay, hands up and come to the 7th. Nobody here. Okay, so that means so that means if we've got people going to the next one, then they have no idea that this went down. So maybe we should keep.
Well, we don't need to cancel it. We can say we might keep it on, and then we'll talk about it.
Yeah, we'll leave it in a shroud of fogs. That's beauty. Yeah.
If we get 50 new followers, we'll. If people have signed up.
Sounds good. Maybe we can do something different actually, because it's always at the Belgian Beer Cafe.
Oh yeah.
If we're doing it a different same day, maybe we can have maybe we can have an office party somewhere. Does anyone have an office party? Office, they'd be willing to have a Christmas office party. Does anybody want that? I don't know. Is there anybody willing to come to another event in what day is it today? The 3rd? In 7 days? Is that